Welcome to class. Today we look at relations in linear algebra. So we'll be going through some of the questions that I gave in my continuous assessment test of November 2023. The first question is a total of 8,500 shillings, these are Kenya shillings, was invested in 3 interest-earning accounts. The interest rates were 2%, 3%, 6%. If the total interest for the year, 1 year, was 380 Kenya shillings, and the amount invested at 6% was equal to the sum of the amounts in the others, calculate how much was invested in each account. So for this particular question, we come up with equations, which we then solve using any of the methods we know, either by Gaussian elimination or Gauss-Jordan, or even by Cramer's rule. So it's you to choose the method you want, but first of all, coming up with equations. So let's see how to come up with equations. We are told that a total of 8,500 shillings was invested, and it was invested at 2%, 3%, and 6% interests. So that is where we get the first equation. So we just say, let the amount invested at 2% be X, the amount invested at 3% be Y, and the amount invested at 6% be Z. That means we invested a total of X plus Y plus Z, and that should equal to 8,500. This is our first equation. Now, the second equation involves the interest rates and the amount that was invested. We are told that it is simple interest. And we know simple interest is calculated by principal amount times rate times time over 100. That means that when you invest X shillings at 2%, and for 1 year, you'll have interest. You'll have earned X times 2 times 1 over 100 interest. And so that is what we do for every amount that was invested at the given interest, and find out how much interest was earned. So let's find out, when we invested X shillings at 2%, what was the interest? The simple interest. So the interest, when you invest X shillings at 2%, would be given by X times 2 times 1 over 100. That is the interest. And that gives us, what does the question say about the interest? Let's just go back and see what the question says about interest. The question says that the total interest after 1 year was 380. That's what I'm seeing here. The total interest after 1 year was 380. That means that when you add the interest that we've gotten, 0.02 plus 0.03 plus 0.06Z, when you add this, you should get 380. That gives us the second equation. And then the third equation, we go back to our question and see what it says. The question says that the amount that was invested at 6% was equal to the sum of the amounts in the other 2 accounts. And so that is what we use to get the third equation. So how much was invested in the other 2 accounts? We had X, which was invested at 2%. Then we had Y, which was invested at 3%. And then we had Z. Z was invested at 6%. So what the question is therefore saying is that X plus Y equals to Z. X plus Y is equals to Z, which we can also write as X plus Y minus Z is 0. That is our third equation. So we now have the three questions, and we want to employ any of the methods we've learned in our class to solve. I'll reduce this system to echelon form, but you can use any other method and get the same result. So what we have as the system of linear equations? We have this system. The system of linear equations is this. Now I want to reduce this system to echelon form. First of all, I extract the augmented matrix by just extracting the coefficients. The first row, the coefficients are 1, 1, 1, then 8, 500. The second row and the second equation gives us the second row where the coefficients are 0.02, 0.03, 0.06, and then 380. The third equation gives us the third row. So we extract the coefficients 1, 1, negative 1, 0. And this is the augmented matrix. This is the augmented matrix. Now, so we reduce this augmented matrix to echelon form by performing some row operations on it. So what I'll be doing is that I want to remain with this element as the only non-zero element in the first column. So I make everything else in the first column to be 0. So how do I make this position to be 0? To make this element to be 0, I will take the second row minus, second row will be obtained by taking the current second row minus 0.02 of row 1. Row 2 minus 0.02 of row 1. So that means at this point, I take the point in row 2, which is 0.02, then minus 0.02 of the value in row 1, the same column. Row 1, the same column, the value is 1. And so that gives me 0. And so that is the 0 you're seeing here. It's the 0 you're seeing in this second row, first column. Then what about at this point? I will take 0.03 minus 0.02 times the element in row 2, column 2. Yeah, it's row 2, column 2. Row 2, column 2, this element here. And that gives me 0.01. It's the 0.01 you're seeing. Then I do the same for these other elements. I take 0.06 minus 0.02 multiplied by 1. That gives me 0.04. And it's what you're seeing here. Then here I take 380 minus 0.02 multiplied by 8,500. That gives me 210. And that's the 210 you're seeing. Now, I also want to obtain a 0 in this position. That is row 3, column 1 position. This position, row 3, column 1. How do I get a 0 there? I'm using these elements here. I have row 3. I want row 3. So I'll take the current row 3 minus row 1, the current row 1. So this 1 minus this 1 gives me this 0. This 1 minus this 1 gives me this 0. And this negative 1 minus this 1 gives me negative 2. That's the negative 2 you're seeing here. And then at this point, I have 0 minus 8,500, and that gives me negative 8,500. Now, I've achieved what I wanted. What I wanted was to have 1 as the only non-zero element in the first column and have zeros elsewhere in the first column. Now, the next thing I want to use the element in this second row, second column, this element, to obtain, I already have a 0 there. I already have a 0 here, so there's no problem. I already have a 0. So if there would be, this would not have been a 0, I would have used this element to create a 0 in this position. But fortunately, I already have a 0 in that position. That means the way this matrix is, it is already in echelon form. This matrix is already in echelon form, so I can just go ahead and solve. But what I did here, to get this other matrix, I just made this element to be positive. I needed this to be positive, although it's not compulsory. I did that by dividing this entire row 3 by -1. When you divide the entire row 3 by -1, you get +2, and then +8,500. And I also thought, so once you're here, you solve this from the bottom going up. You solve this from this bottom going up. And you know what this last row means? It means 2z is 8,500. 2z is 8,000. That means 2z is 8,500. That's what this last row means. And this other row means, here it was x, y, z. So it means y plus 4z is 21,000. 21,000. And the first row here means x plus y plus z is 8,500. So you're solving from the bottom going up, make z the subject of the formula by dividing by 2 both sides. Once you get z, come to this second equation and substitute that z with. Then make y the subject of the formula. Then that will give you y, and you had already gotten z. So with that y and z, substitute them here and make x the subject of the formula to get the value of x. So I already done that. Let me see what I got as my result. So when you solve going up, you get z to be 4,250. Then y will be, substitute z here. Let me just do it for the sake of those who may not have understood what I'm talking about. Once using this last equation, dividing both sides by 2, if you divide both sides by 2, you get z to be 4,250. Then you move this second equation. This second equation, you have y plus 4, but what is z? Z is 4,250, and that should give you, is supposed to be 21,000. Yeah, let's just go back and see what it was. It was 21,000. 21,000. And then, what is y? Y would be 21,000 minus 4,000 multiplied by 4250. I was getting this to be 4,000. Then you move to this upper equation. What? And it begins with x. Says x is, no, x would be 8,500 minus y minus z. But we know what y is. We know what y is 4,000. And we also know what z is 4,250. And so that will then give you the value of x which is 250. It is 250. So that's how you then get those values. And that's all the question wanted. The question wanted us to find how much was invested at 2%, and that was X. How much was invested at X%? No, Y at 3%, and that is Y, which is 4,000. How much was invested at 6%? That was Z, which is 4,250. Let's look at the next question. The next question, a transformation in three-dimensional space is defined by the following 3x3 matrix, where Y is a scalar constant. If the determinant of M, this one we said that these vertical lines here would mean determinant. These are two vertical lines. So if the determinant of M is 0, find the three possible values of Y. So what that means is that we just get this determinant, the determinant of M of this matrix, and then equate to 0. And then when you equate that to 0, you find the value of Y. And again, we learned several ways of getting determinant of matrix. So we'll expand along this row 1. Because row 1 has a 0, so it becomes easier for us to do it along this row. It would also have been easier for us to do it along this column because this column has a 0. So it would be also easier to do it along this column. But of course, you can still do it along any row and along any column and find the same result. Let's expand it along the first row. So you take this element, the first element here, and then multiply by the determinant of the matrix that remains when you delete the row of this element and the column of this element. When you delete the row of this element and the column of this element, the Y negative 2, Y negative 1, Y negative 1. So the determinant of that matrix that remains. And then minus, it will be minus 2 multiplied by the determinant that remains when you delete the row column of 2 and the row of 2. When you delete the row of 2 and the column of 2, you are left with 1, negative 1. You're also left with the negative 2 and Y minus 1. So the determinant of that matrix. And that's what you see I've written here. But now this plus is as a result of this negative. That gives you plus. Then the next one is not important because we have a 0 there. So anything multiplied by 0 would be 0. But what was it? It is plus 0. 0 multiplied by the determinant of the matrix that remains when you delete the column of 0 and the row of 0. That matrix that remains is this. There's a Y. There's a Y and a Y minus 1. And that's what you see. But now this will be 0. That is why I said it's easier for us to do it along a row or along a column that has zeros because it makes our work easier. Now, so let's now find those determinants. And you know how to find the determinant of this matrix. You're multiplying this or this diagonal. And that's what I did. Y multiplied by Y minus 1. And then it's supposed to be minus, but there's a minus 2 here. So let's see how it works out. Because I've written positive, and you'll see how that positive comes in. Supposed to be minus 2 multiplied by this element, which is Y minus 1. So this minus and this minus is what gives me this positive. So it's positive 2 into Y minus 1. So that is the determinant of this first matrix. Just clear this. So the determinant of this matrix is this. Then multiply that. Now let's come to this. You have these two. Then now the determinant of this matrix would be 1 multiplied by that, which would be y minus 1. Then minus this product of this diagonal, which is 2. So what I then get is just y minus 1 plus 2, which is y minus 3. And let's simplify this inside this bracket, curly bracket. I have y square here. This is y square, and this is negative y. That's what you're seeing here. And that is 2y minus 2 when you multiply. I'm just multiplying outside, expanding this bracket. And that's what we have here. Now we can also simplify further. And what I did, in fact, was to factorize. Because I'm saying this part, this number of terms. Because there are this number of terms. Y square minus y plus 2y minus 2. That's what I've written here. Y square minus y plus 2y minus 2. Then it goes here. Y minus y goes here 2 times. And that's this. Let me just erase this first of all. And then I show what I did. When I equated that to 0, so when you equate to 0, and then you also realize that this other bracket can be simplified. How do you simplify this bracket? This bracket here, I will have y square negative y plus 2y. That gives me y. And then negative 2 plus 2, that gives me 0. So this bracket simplifies to this. And so I have this y minus 1 multiplied by y squared plus y. And this, therefore, I can also factorize this. I also factorize this. Because this is the same as, this part is the same as y plus 1 multiplied by y. So y is common, it can be factored out. And that's why you're seeing I've written it here. So I have this y minus 3 is here. Then this one, I've just simplified it further, factorized it to this. That's what I've written. And then I equate to 0. So when you equate this to 0, that either the first part is 0, the first part is 0, which will mean that y is 3. Which will mean that y is 3, or the second part is also 0, which is y minus 1 is also 0, which will mean that y is 1, or the last part, y, is also equal to 0. That is why you find the results for y to be 3, negative 1, supposed to be negative 1. It's only supposed to be y plus 1. Y plus 1 is 0. So it will mean that y is negative 1. So y is either 3 or negative 1 or 0. And so that is how that question was supposed to have been done. We'll look at the next question. And the next question again is about matrices and inverse. It says the 3 by 3 matrix A is given below, and if its inverse is this, what would be the value of D and E? So this question, it just means that you find the inverse of this matrix. Then after finding the inverse of this matrix, factor out 1/9 what would be inside this bracket? What do you find inside this bracket? Just pick out D and E from what you have inside the bracket. So the first thing we do is to find the inverse of this matrix. And again, we have various methods of finding the inverse of matrix. I showed you various methods. I showed you how to find the inverse of this matrix using the method of adjoint, where you get the cofactor matrix first, and then get the adjoint of the matrix to find the inverse of this matrix. And the other method was where you have the matrix, and that's the method I'm using, using the Gauss-Jordan elimination, where I write this matrix and I augment it with the identity matrix. I augment this matrix with the identity matrix and then perform row operations on those two matrices so that I transform the matrix on the left to identity matrix. And so our identity matrix, which was on the right side, would then be transformed the inverse of this matrix. That's what I was saying. We use Gauss-Jordan elimination where we augment the given matrix with the identity matrix and perform row operations to transform the matrix on the left to identity matrix so that the matrix on the right side becomes the inverse of this matrix. Let me show you what I did. Let's see what I did. Just a minute. So I write my matrix on the left side and then the identity matrix on the right side. And I perform row operations so that this matrix on the left becomes identity matrix. Those row operations I'm performing on the entire matrix as it is. After this matrix on the left, whatever will be here will be the inverse of the given matrix. So, how do I write the identity? We know what the identity matrix is. We know that we require a 1 here. We require 0, 0. We require 1 here, where there's a 5. So how do you get a 1 where there's a 5? We can do that by dividing the entire row 1 by 5. That's what I did here. Divide row 1 by 5. When I divide row 1 by 5, this is what I get. Now, I've not touched row 2 and row 3. That's what I did. So let me just scroll down. So I said I would take row 3 minus row 1 to get row 3. So just subtraction. This is just subtraction. This 1 minus this 1 gives me 0 here. This 0. This 3 minus 2 over 5. The LCM will be 5. The LCM will be 5. And this will be 15 minus 2, and that is 13 over 5. That's what you're seeing here. And then for this one, I have 1 minus a fifth. 1 minus a fifth. The LCM will be 5. And that'll be 5 minus 1. That gives me 4 over 5. So I do it for the entire row, and that's what I get. When I subtract the entire row 3 minus the entire row 1 is what I get. Now, so I now have the 0 here. I've achieved what I wanted in the first column. Because I want this matrix to be identity matrix. So that means I want a 1 here. Luckily, I already have it. Then I use this 1 to create a 0 here and a 0 here. So I want a 0 in row 1, column 2 position, and in row 3, column 2 position. That's why I want 0s. How do I achieve a 0 in this position? I need a 0 in row 1. So I would take the current row 1 minus 2 out of 5 of row 2. And that's what I wrote here as my row operation that I'm supposed to carry out. I also want a 0 in this position. I want a 0 in row 3. So I take the current row 3 minus 13 out of 5 of row 2. That's what I wrote here as the operation I would be carrying out. So, and then you are familiar with this kind of operations. It's easy to do, just subtracting. I'll just show one and then you do the rest. I'll just show you one. Let me show you how I got this negative. Here, so I want just to show you one, how I obtained this 0 from here. Then how I obtain this negative 1 out of 5. Then you do the rest for 1 and for 3. Now, so at this point, what I have row 2. I'm using this. I have row 1. The element in row 1 is 2 out of 5 minus 2 out of 5 of the element in row 2, which is 1. So that gives me 0 here. Now what about here? The element here is 1 out of 5, then minus 2 out of 5 of 1. 2 out of 5 of 1. So this will be the same as negative 1 out of 5. That's what you're seeing here. And you can do that. You can just follow these elementary operations. And of course, you've learned them in class and perform for the entire matrix. Now, let me just delete this so that we go to the next step. The next step, once you've achieved here, because what we wanted was to have a 1 in this position and then 0 elsewhere in that column, this column 2. Now, what now follows is to have a 1 in this position and zeros elsewhere in the column. How do I achieve a 1 here? Multiply the entire row by negative 5 out of 9. The entire row 3 multiplied by negative 5 out of 9 will give me a 1 in this position. So let me just see what we did when I multiplied that. So when you multiply the entire row by negative 5 out of 9, here you get 1. And then at this point, you have negative 1 out of 5 times negative 5 out of 9. And that gives you 1 out of 9. That's what I have. What about here? What about here? You have negative 13 out of 5 times negative 5 out of 9. And that gives, this cancels. There's a negative and a negative. That gives you positive 13 out of 9. Negative positive 13 out of 9. So that's what you get. And you do for the other elements. Now, to achieve this, what you want is now to have a 0 here and a 0. How do you get a 0 here? This one is easy. To get 0 in row 2, just take row 3 minus row 2. That's what I have written. Just take row 2 minus row 3. And to get a 0 in row 1, take that row 1, and then minus 1 out of 5 of row 3. This minus and that, this other one will give you positive. So you have row 1 will be obtained by row 1 plus 1 out of 5 of row 3. So now when you do these operations, this is the matrix you get. And you'll have achieved that the matrix on the left now, as we wanted, is the identity matrix. Has now become the identity matrix. This matrix has become the identity matrix. That means the matrix here now is the inverse of the given matrix. So that's why I've written that the inverse of A is, and I've written here, that the inverse of A is what? Is this matrix. So this is the inverse of A. So we only need to factor out 1 out of 9. When you factor 1 out of 9 from this element, you get 2. Here you get -1. You get -1, -1, -4, 5, 1, 13, -5. So just put 1 out of 9 outside and you have this matrix. And that's why from this matrix now they're asking you what is E and D. So D is 5 and E is 13. Because you just compare this matrix here. This matrix, compare it to the one given in the question and get what E and E are. The one given in the question is this. This is the matrix in the question. Now, so we can move to the next question. Question 4. Talks of an invertible transformation in a 3-dimensional space being defined by 3x3 matrix, and it has an R, which is a scalar. So the question is, find the possible values of R. Now, this question, for you to do it, you must know what this means. Non-invertible. It means this matrix here has no inverse. When do we say that a matrix has no inverse? A matrix has no inverse if its determinant is 0. If the determinant of this matrix is 0. And non-invertible. So that means this matrix, it has no inverse. Non-invertible, that's what it means. It has no inverse. So it has no inverse if the determinant is 0. So that means just find the determinant of this matrix, equate it to 0, and make A the subject of the formula. And that will give you the value of A that the question wants. That is why I did find the determinant, and I did that along the first row. Along the first row, element A multiplied by the determinant of the matrix that remains when you delete the row of A and the column of A. So that is -1, A, 4. That's what I've written here. Then there is a negative. There's a -1. That is the -1 you see. Multiplied by the determinant of the matrix that remains when you delete the column of 1 and the row of 1. So you are left with the 2, 3, F4. 2, 3, F4. Then plus 2. Plus this 2 multiplied by the determinant of the matrix that remains when you delete the row of 2 and the column of 2. When you delete, the matrix that remains is 2, 3, -1, 2, 3, -1, A. Now, this is the determinant of this matrix, equated to 0. Equated to 0. And we know how to get the determinant. This would be -4 minus. So we multiply this diagonal minus this, the product of this diagonal. The product of this diagonal is -4. And the product of this other diagonal is A square. So -4 minus A square multiplied by this element And then minus 1, this product is 8 minus 3a. That's what we have here. Then plus 2, this product is 2a. No, this product, this diagonal here. This one is 2a, and this is negative 3. So I have 2a minus negative 3. That gives me 2a plus 3. That's what we're seeing. Equal to 0. Now you can simplify this. Of course, this is negative 4a. A square, a cubed. And then this other one is negative 8. This other one is positive 3a. Just multiplying those elements with the one after the bracket. So this one give us 4a, and this will give us 6. So when you open those brackets, that's what it gets. Now collect like terms and try to simplify and see what you get. Yes, collect like terms, and of course I'm seeing some like terms like 3a and 4a, and then negative 4a. That will give me 0. They give me 3a there. Because this and this will be 0. Negative a cubed has no other like term. So negative a cubed. And then this negative 8 and positive 6 would be negative 2. And this would be 3a equals to 0. Of course, I can multiply by negative 1 to get what I have here. Multiply the entire equation by negative 1. I get what I have here. I get a cubed minus 3a plus 2 equals to 0. This is a cubic equation which we solve to get the value of a. So we get the factors for this equation. How do we factorize such an equation? To factorize this equation, we look at the coefficient of the unknown with the highest power, and then the coefficient of the constant. The coefficient of this and that constant. So the root to this equation is likely to be r over s, where is r over s, the root or the solution to this equation is % of the unknown with the highest power. Factors of, so that's how I've written here, that the factors of this equation are in the form r over s, where r are divisors of the constant term 2, while s are the divisors of the coefficient of the variable with the highest degree. In this case, the variable with the highest degree is a, so its coefficient is 1. So what are the possible r? What are the likely to be r? R are factors of 2, which are likely to be plus or minus 1, plus or minus 2. Those are the numbers which can divide this constant. This is r. R is likely to be this. And then the numbers are divide 1. Our s is likely to be plus or minus 1. So the root for this equation, therefore, is when r is, so you see that this r can be 1, negative 1. If I just write it, it's negative 1, 1, negative 2, 2. And this s is just negative 1 and 1. So I can take this s and divide into this. If I take this s and divide into that, into r, my r over s is likely to be, if I divide this s into s, which is -1, and divide it into r, which is the r result, so then I'll be having +1, -1, +2, -2 as the likely roots. I can also take s to be this one. So if I take s to be that one, then what would be r? It would be what would be r over s? R over s is would be -1, 1, -2, and 2. I'm just dividing this one into these elements. So my roots then are these. 3 of these are my roots. 3 of these, but you can see they are the same roots here. -1 is repeated, is here and is here. +1 is repeated, is here and here. 2 is repeated. So it means that my likely roots, therefore, are just 1, -1, -2, and 2. So I try to check which of these will be a root. I try using this equation to see which one will be a root. So I just plug 1 where there is a and see whether it will give me a 0. So I'll be having 1 cubed minus 3, 1, and then plus 2. And this would be 1 minus 3, which is -2. This would give me 0. That means a is 1. So 1 is a root. You can try the rest and see which other 2 will be roots to this equation. But that is not the root I've taken. The root I've taken is, after getting this 1, I've used long division to factorize this equation, so that I then get the quotient and factorize the quotient again. So that's the root that I've taken, and is the one I'll want to show. The one I want to, I know you know to use long division, and it's what I've used here. So after obtaining that a was 1, I just took this one the other side and came up with 1 minus a. And this is what I divide into the equation that I'm given, -3a and then +2. Then I ask myself, how many times does a go into a cubed? And a will go there, a square. Because a square times a will give me a cubed. And then a square times -1 will give me -a square. And as we do in long division, I would subtract this from the one above. Subtract from the one above. So I'm just subtracting. Subtract. So when I subtract, this becomes minus, and this becomes plus. So that's why I just add these equations. I don't know whether you've gotten what I've said. Let me just remove those signs again. I just said, subtract this from this. That will give you 0. And here, above here, we do not have a square. So it's the same as saying plus 0a squared. Plus 0a squared. So there's a minus here. So I have 0a squared minus a squared. No, but minus a squared. It's minus s. Because I'm subtracting this from that. That gives me positive. So this means this would be a square here. It will be a square here. Then bring this one down. It's -3a. Ask myself, how many times does this a go into? Again, subtract this second equation with the upper equation. A square from this A square will be 0. What about here? I have 3A minus A. Now I have negative 3A minus A, which gives me negative 2A. Then bring this one down, positive 2. Ask myself, how many times does A go into negative 2A? It will go into negative 2A negative 2 times. Negative 2 times this would be negative 2A, and then negative 2 times that would be positive 2. And subtract the bottom equation from the upper equation to get it. And you subtract to get it here. So I have divided, and that's what I did here. So I did here. The only difference you're saying is that at this point, when I was subtracting, this was minus, so it became minus, and this subtracted, it becomes positive. So I was just changing these signs. Because I was subtracting. Now, so what have we found? We found that A cubed minus 3A plus 2 can be written as A minus 1 multiplied by the quotient, which is A squared plus A minus 2. So this one, you can also factorize it. That one, you know how to factorize. So let me just now take you to what I wrote after that, because I know at your own time you know how to factorize this other question. But of course, I've factorized it for you also, so that you just confirm. I say that this part is also the same as this when you factorize. So then what I now have is A minus 1 times A minus 1 times A plus 2 is equals to 0. So that what does that give us? Equate this part to 0, which it means that A will be 1. Equate this other part to 0, it means again A will be 1. And equate this other part to 0, it means A will be A is supposed to be negative 2. A is supposed to be negative 2 and equate the other parts. We just factorize it. We have A squared plus A minus 2. You look for two values whose product is negative 2A squared, whose product is that, and whose sum is A. What are those two values? The sum should be A and the product should be negative 2A squared. That means those two values are negative A and positive 2A. So that you have A squared minus A positive 2A minus 2. And when you factorize this, what do you get? When you factorize this, you have A into A minus 1 plus 2 into A minus 1. And so this will give you A plus 2 and A minus 1. That means what I had written here is correct. And so if this is correct, when you equate this part to 0, then this will be negative 2. It should be negative 2. That's what I wanted to confirm. Question 5. The 3 by 3 matrices A and B are defined in terms of scalar constant K. Find the 3 possible values of K such that AB is singular. The product of these two matrices is singular. What does it mean by singular matrix? Matrix is said to be singular if its determinant is 0. If the determinant of AB is 0, then it means that AB is a singular matrix. If the determinant of any matrix is 0, then that matrix will be singular. So that means for us to do this question, we just get the product. That's one way. Get the product of these two matrices and then equate to 0. Now get the product of these two matrices, and then the determinant of these two matrices equal to 0. The determinant of that product equal to 0. Now we know how to get the product of matrices. We're multiplying a row and a column as you add the results. Multiply a row of the first matrix times a column of the second matrix and add the results. So let's see. I'll just do one row and one column. K times 1 will be K plus 9 times K, which is 9K, plus 2 times 4, which is 8. And that gives me 10K plus 8 as the first element here. As I've got that. Then let me see. Now the first row times the second column. The first one, the second column. K times negative 3 would be negative 3K. 9 times 2 would be 18. We are adding the results. Then 2 times 1 would be 2. And so when you add this, you get this is 20 and this negative 3K. That's what I got this. You do for the other elements. Of course, you know how to multiply matrices. Now, so after multiplying those two matrices, we have what our AB is. Our AB is this. Now, this determinant equate to 0 because we were told that this AB was supposed to be singular. Equate this determinant to 0. Now, so that means we must get the determinant of this matrix. I did along the first row. What is the first element in that first row? The first element is this. Is what I have here. Multiply it by the determinant of the matrix that remains when you delete the row and the column of this first element. So the determinant of the matrix that remains is 2K minus 3, 2 minus K, negative 16, then 12. That's what I have here. Then come to the cement. I'm doing it along this row. This is second element. That's what I've written. It's minus the second element. Minus. So then delete the row of this element and the column of this element. The matrix that remains is K squared plus 1, 9 minus K, 2 minus K, and 12. That's what I have here. Then come to the next element. Now, the third element here, as we all can see, is, let me just delete this first. This is our third element, 2K minus 7. So it's plus times the determinant of the matrix that remains when you delete the column of this element and the row of this element. And so the matrix that remains is K squared plus 1, 9 minus K, 2K minus 3, and then it's negative 16. That's what we have here. So this gives you the determinant of this matrix. Equate it to 0. Equate that to 0. But of course, we can get the determinant. We know how to get the determinant. When I multiply this diagonal, I get 24K minus 36. I'm getting the determinant of this matrix. So this is 24k minus 36. What about this? It is minus into minus 16 multiplied by, this is 32. Oh, I put minus. Let me just, because some people get confused. We just say minus and then open the bracket. Minus 16 is that to be negative 32. And then minus 16 times minus k will be 16k. Now open this bracket. You have 24 at this point, 24k. It's 24k. And this other one, oh, it's minus 36. Now open this bracket. You have plus 32. And this should be negative 16k. Now, how do I arrive this bracket? 24k minus 16k gives me 8k. And then negative 36k plus 32k, that gives me negative 4k. Now, you do again for this. You do again for this. These are the brackets. Do for these are the brackets. These are the determinant. Then these are the determinants. And see that you obtain what I have. Now, after this, you just open the brackets. Open the bracket and collect like terms and see that you arrive at this. What I mean is this, multiply this by that. You have 8k. This times that, you have negative 40. Okay. This and that, you have 64k. This and that, you have negative 32. Come to this other one. There's a minus 20 times this. You have 220 k square. 20 times this. You have 22k, 220k, and so on. You know how to do this. Simplify and arrive at this cubic equation that I want again to show you how to get its factors as we did for the earlier example. Now, so once you are at this cubic equation, want to get the factors of this cubic equation. And the factors of this cubic equation, as we had already stated in the previous example, would be written in the form R over S, where R are factors or divisors of 11. The divisors of 11 are plus and minus 1 and plus and minus 11. And S are factors of this constant that has an k with the highest power. So the factors of this 5 is plus and minus 1 and plus and minus 5. So that means the factors, therefore, R over S is likely to be, if I divide this into this, I would have plus and minus 1, plus and minus 11. If I divide by 5, I would have plus and minus 1 out of 5 and plus and minus 11 out of 5. So these are the likelihoods. So again, we use inspection. We try positive 1, try negative 1, try positive 11, try negative 11, try. So you try until you get 1. Once you get 1 that is a root, use long division. So you try those and see which ones is a root. Once you get one of them, this long division. So on inspection, I found that -1 was a root. Because when you put -1 here in this equation, you would get -5, -51, plus 45, plus 11. And this is supposed to give us 0. Because this would be 56 and this is -56. So that gives us 0. Now, so then we found that k is -1 is a root. So we just take this -1 the other side. K +1. And divide this into 5k cubed minus 51k squared minus 45k plus 11. And ask ourselves, how many times does k go into 5k cubed? And we got there 5k squared. So that 5k squared, write it here. Multiply by that, 5k cubed, and then plus 5k squared. I subtract the bottom equation from the upper one. This part you get a 0, and this other part you get -56k squared. So do the same thing, and you get this as the quotients. Get that as the quotient. So that means the cubic equation given to us can be factorized as this. We found that can factorize this was the quotient. So we try again and see if this can be factorized, this part. If it can be factorized, this part is easy. This is a quadratic equation. So that means the cubic equation, therefore, can be factorized this way. Now, equate it to 0. When you do that, you will find that k is -1, or k is 11, or k is 1/5. So just equating this part to 0, then this part to 0, then this part to 0, and then get this values. That is one method. The first method, when I saw that the question said that the product was to be, the product AP was to be singular matrix, I thought, let me just multiply these matrices, get the determinant and equate it to 0. Now, the other method is when you realize that this determinant of AP is the same as the determinant of A times the determinant of B. Is the same as a determinant of that is the same as a determinant of A times the determinant of B. So now get the determinant of A. There are very many methods. You can even write this k times the determinant that remains when you delete the row and the column of k, and then -9 times the determinant that remains, or the matrix that remains when you delete the row of 9 and the column of 9, and then plus 2 times the determinant of the matrix that remains when you delete the row of 2 and the column of 2. That is one way. The other way is what I did. I saw a 0 here, and I thought I should introduce another 0 and make my work easier. So, we already discussed this and say that whenever you have zeros, your work is easier. So, I thought of how do I create a 0 here? To create a 0 here, I want row 1 minus 2 row 3. Row 1 minus 2 row 3. So this point minus this would be k minus it's row 1 minus 2 row 3. So 2 times this will be 10. 10 from this will be k minus 10. 2 times this would be 2. 2 from this, no, it's negative 2. Negative 2 from this would be 11. 2 times this would be 2. 2 from this would be 0. So I have these 2 zeros and I have this matrix. So now I can get a determinant along this column that has more zeros. And you know how it goes. When you are doing a determinant, this element you add is plus, then minus, plus, minus, plus, minus, plus, and so on. So they alternate. So if this is plus, this will be minus. This will be plus. So if this is plus, then this will be minus. So if this is minus, then this will be plus. So this is the element, the only element, non-zero element here. So 1, and it's plus. If you say plus, minus, plus, minus, plus. So delete the row and the column of 1. You're left with k minus 10, 11, 1 minus k. No, 1, then k. So the determinant of this product minus this product. So that is k minus 10k minus 11. It's k squared, then you multiply k squared minus 10k, then minus 11. That's what I have. That's what I have. This can also be factorized. You can even factorize it further, because it can be factorized. Now, after that, after factorizing that, you now get the determinant of B, because I factorized it here. Let's now go to P and find the determinant. I thought that using the second row, I can get a 0 here. By taking row 1 plus 2 row 2. And using this second row, I can also get a 0. By taking row 3 plus row 2. So that gives me this matrix. So I get when I do this elementary row operations. Now, so that means this, I have a zeros in this column. I can get determinant along this column that has zeros. This will be plus, minus, plus, then minus. So I have minus, minus 1. Delete the column of negative 1 and the row of negative 1. What you are left with is 1 plus 2k, then 1, k plus 4, then 3. Get this determinant. And I already did that for you. Just do it, and then compare the results. Of course, you do it and simplify. Now, so we had the determinant of A, and we now have the determinant of B, and we note that the product of those, the product of the determinant of AB is the same as the determinant of A times the determinant of B. So the determinant of A is this, times the determinant of B, which is this, equal to 0. Equal to 0 and find the values of k. Question 6. Here we are given a system of linear equation, and we are told that when you apply Gaussian elimination, the result would be as shown here. So the question is, what is the value of x, y, and z? So what this question is asking us just to write the augmented matrix for this system and then reduce to echelon form. Reduce to echelon form and then compare your result with this and extract x and y from your results. So I wrote the augmented matrix here. This is my augmented matrix. And I know how to reduce to echelon form. I want to maintain this 2. Why am I maintaining that 2? just go back to my question and see why I'm maintaining my 2. The result that I was told, the result has at least 2 maintained. So that's why I maintained the 2. And you can see that this other row has a 3. So if I get a 3, I'll maintain. Or I'll create a 3. Or if it comes naturally, then I'll maintain it. If it doesn't come naturally, then I'll try to create it. In this other row 3, I have -1. If it comes naturally, I'll maintain it. But if it doesn't, I'll create it. Then this other row, I have 2. And again, if it comes naturally, I'll maintain. If it doesn't, I'll create. So that means this now reduced to 1. We want to use this 2 to create a 0 here, in this position, create a 0 in this position, and create a 0 in this other position. To create a 0 here in row 2, you can see that I need this current row 2 minus 2 times row 1. Because 2 times this from this, you can see. But I've been doing it for the entire row. And to get here, row 3, a 0, I'll take the current row 3 just plus row 1. And I'll get a 0 in this position. And to get a 0 here, which is in row 4, I'll take the current row 4 minus 2 row 1. So this is what I've written here as the operations that I want to perform. Those are the operations that I want to perform. So I'll just do one row and then you do the rest. This times 2 from this is 0. And you see that is 0. This times 2 will be 2. From this is a 3. This times 2 would be -2. So I have -3 minus -2, which gives me -1. And then this times 2 would be 4. From 6, that would be 2. This times 2 would be 10. From this, I have -1. I've done for row 2, you do for the other rows. Now, so we've achieved what we wanted in the first column. And we can see that the 3 has already come and we maintain it because it's in our question. Now we use this 3 now to create a 0 in this position and a 0 in this other position. How do I create a 0 in this second row, in the third row? I have the current third row minus 2 row 2. That's what I have here. And I want a 0 in here, which is in row 4. I take the current row 4 minus 3 row 2. That's what I have here. And again, I'll do for one row, and you do the other one. So row 2 remains the way it is. Row 1 remains the way it is. Row 2 also remains the way it is. But I want a 0 here. So this times 2 from this gives me that is 0. This times 2, I have -2. Subtract from -3, I have -1. This by 2 will be 4. From this 8 gives me 4. And then -1 times 2 will be -2. Subtract from 9 gives me 11. So I've done for that row. You do for the other row. Now, so I have this one, and it's in my question, so I maintain it. I want to use it to create a 0. That means I just have to subtract. I love to subtract row 3 from row 2, from row 4. Supposed to subtract. subtract row 3 from row 4. That gives me a 0. So, -1 minus -1, I get this 0. -2 minus 4 why is it minus 0? You confirm whether this value, okay? You confirm whether this value is minus or positive. This value. You try and confirm whether it's minus or positive later. No, I think it's okay the way it is. I think it's okay. Let's just use it the way it is. But you go through slowly and see. So I have this. No, this value is not correct. It's either this one or this one. One of them is incorrect, but you check. -1 is 11. You'll check these two rows, but then the result here is okay when you do it, because we wanted X, Y, and Z, and so you're just comparing this matrix with the one given above. Just compare this matrix with the one given above and see the value of X, Y, and Z. Now, from there, we're also supposed to get A, B, and Z. Is it A, B, and Z or what? Just go back to the question. A and B. Were in our equations. They were in the equations. So after reducing the given form, this is what we have. This will be A, B, C, D, 2A plus B minus C plus 2D is 5. That's what it means. So the last row means, the last row here means what? The last row means 2D is 6. So this means that D is 3. That's why I got that 3. Then you are solving going up. You're solving going up. Come to this equation. A, B, C. So this is -C plus 40. Plus 40 is 11. But we know what D is. D is 3. So it's -C plus 12 is 11. So that means -C is -1, which means C is 1. You solve for the rest going in. You solve for the other elements as you move on. So the other elements A and B, of course, are up. We solve going in them. But we found D to be 3 and C to be 1. So, and I've solved for you just to do it and compare your result with mine. Let's look at this question 7. Compute the determinant of the following matrix. This is very easy. You look at the relationship of the rows and the columns, and you can see that one row is a factor of the other row. For instance, when you factor 3 out of row 2, you get row 1. That's what I did here. So when you find that one row is a factor of the other row, then it means the determinant of that matrix is 0. Or when you find that one column is a factor of the other one. For instance, when you multiply this column here by B, you get this column. So that means the determinant of those matrices is 0. Just the same way, if I have this row, and then multiply this row by an element 3 and get 6, 12, I expect this determinant to be 0. Because this row and this row are related, one is a factor of the other. And that's what I've written here. I've said, note that if any row or column is a multiple of the other row or column, then the determinant of that matrix is 0. So once you know that, it becomes very easy. If you don't know that, you can just work out this, because you know how to work out determinants. And again, I've done that for you. I've assumed I don't know that rule. So I wanted to work out along the row 1 times the determinant of the matrix that remains when you delete row 1 and column 1. This is what you get. And then minus b times the determinant of the matrix that remains when you delete row 1 and column 2. When you do that, you get 0. Let's look at question 8. Consider the following system of equations. For what value of k does the system have no solution? And for what value of k does the system have an infinite number of solutions? As we have discussed in our class, we say that a question of this kind, what you do is to reduce the system to echelon form, and then look at what happens in the first matrix. And look at the last row or any other row, look at what is happening in those rows after reducing to echelon form. So I reduce this matrix to echelon form. I extracted the augmented matrix first of all. I want a 0 in, I want k, the first k there, to be the only non-zero element in the first column, and the rest to be zeros. So how do I get the zeros? We get a 0 here. 1 minus 1 out of k of row 1. Row 2 minus 1 out of k of row 1. That's what I've written. And then to get a 0 here, I take row 3 minus 1 out of k of row 1. And again, that's what I've written here. Now, so we just do that. The first row remains what it is. Then multiply this by 1 out of k, I'll have a 1. Subtract from this, I have a 0. I'll do 1 row. And then the second element, k, minus 1 out of k of 1. The LCM is k, and this would be k squared minus 1. Or you can just leave it. In fact, I just left it this way. I just left it k minus 1 out of 2. Now, so I just left it as 1 minus k. But you would still have simplified it if you wanted. Now, these are the elements, again, these are the elements modeled by 1 out of k and subtract it from 1. You can leave it like that, or if you want, you can say the LCM is k, so it will be k minus 1. That's what I wrote. You can simplify it. Then the last element, 1, and again that will give me this. You do for this other row. You do for this other row. Now, after that, I want to leave this element the way it is, but you can make it 1. Even this one will have made it 1 if you wanted. And if you would have made it 1, you would have gotten, this would have been 1k, 1 over k, 1 over k, 1 over k. And so you subtract here. You just have subtracted from row 1 from row 2. So this would be k minus 1 over, you just get what you have here. You get what you have here. What would be different only would be that this would be 1, and this would be 1 out of k, 1 out of k, 1 out of k. Now, so this one, leave it the way it is and use it to get a 0 in this position. And take this k minus 1 out of k, the whole of this divided by this k minus 1 out of k, and this result multiplied by 1 minus 1 out of k. Multiplied by k, it's k minus 1 out of k. So this is what I wrote here. This is what I wrote here. This is what I wrote. Because this is k minus 1 out of k multiplied by k minus 1 out of k is what I have here. Then multiplied by row 2. Multiplied by row 2. So that will give me 0 in this position. So the only part that I'm supposed to show you how I came to this is this. And let me show you how I arrived at that. So I have row 3. Row 3 is this element. Let me write it. K minus 1 out of k. Then subtract from it k minus 1 out of k multiplied by k minus 1 out of k multiplied by this row 2. Multiplied by the element in row 2, which is k minus 1, k minus 1. Write it by k minus 1 out of k. So I would then simplify this numerator. I would then simplify this numerator and then come back. Let me simplify the numerator. The numerator is k multiplied by k minus 1. In fact, this k squared minus 1 out of k. You know I arrive at that. Because here the LCM is 1, the denominator is 1. So the LCM will be k. 1 into k times k, the k squared. Then k into this will be 1. So this is what I have. So this is my denominator. And in fact, this denominator simplifies to k squared minus 1. In fact, it can also simplify to k minus 1, k plus 1 when you factorize. Because these are difference of squares. So that instead of this denominator, I can write this. I can write that. So let me just write here what I have. What I now have is k minus 1. No. It's k minus 1 out of k. Then minus, the numerator there is k minus 1. And the denominator is k minus 1, k plus 1. And then multiplied by k minus 1 over k. And of course, you can even decide to divide that. When you do that, you're left with this part is k into k squared minus 1, then minus, this other part is k minus 1 out of k into k plus 1, which is the LCM of these two is k into k plus 1. This one, this k goes here, k plus 1 times. So k plus 1, what about this? What is this? This is k minus 1, k plus 1. This k minus 1, k plus 1. This part. So what I'm saying is k goes here, k plus 1 times. So k plus 1 times this is the same as k minus 1, k plus 1, then this k plus 1. Hope you're writing properly yours. This is k minus 1 times k plus 1 times k plus 1. Then minus. This part goes in itself once. So you have minus k minus 1. And you can see k minus 1 here and k minus 1 here. Those are like terms. Let's factor out k minus 1. When you factor out k minus 1, it will go here. K minus 1, no, k plus 1, k plus 1 times. And then it will go here, 1. So we have minus 1. And then remember our denominator, which is k into k plus 1. So what does this numerator simplify to? The numerator simplifies to k minus 1 into, this will be k square plus k, so let me say plus 2k, and then plus 1, and then minus 1. So this goes like that. And this is k plus 1. Let's get some little space. You know how the ones disappear? You know, when we multiply this, we got plus 1. And then there's this minus 1, that gives us 0. So you're left with this. So what do you have now? What we now have is k minus 1 into k plus 2k. I've just factored k. I've factored k out. Yes. So k will go here k times and go here 2 times. Then the denominator we have is k into k plus 1. So this k will come to this, and then you are left with this. You are left with this. That's how I arrived at that. You will listen to it at your own time, and every time you find that I'm moving faster, you can always pause and listen to it again. Now, what about here? What about here? How did I get this? It is this row, this element, and this element is what? K minus 1 out of k minus k minus 1 out of k into k minus 1 out of k. This result multiplied by k minus 1 out of k. this k minus 1 out of k. Now again, you can simplify this. We had already simplified this part. This denominator, but we can still do it. It's k into k square minus 1 out of k, which is k square minus 1, which is k minus 1 followed by k plus 1. That's our denominator here. So then what we have is k minus 1 out of k minus k minus 1 multiplied by k minus 1 out of k, and this is out of k minus 1, k plus 1. You can see that this can cancel. If it cancels, you're left with k minus 1 out of k. There's a minute. This k minus 1 out of k, then minus k minus 1 out of k plus 1 followed by k. So what is the LCM? K plus 1 out of k is the LCM. This goes here k plus 1 times. So you get k minus 1 multiplied by k plus 1, then minus k minus 1. It's good to make good use of these brackets, because if you don't use brackets properly, then this minus will lose it. Now, so you realize that this element here and this element are same, so you can factor out. K minus 1, factor out of the numerator. And so it go here k plus 1 times, k plus 1 times. And it will go here negative 1 times. Go here negative 1 times. So the pen doesn't want to move to this side. Class, it does not. So it go here negative 1 times. Close the bracket. And this is k plus 1, then k. Now what is inside this bracket is k. It is k plus 1. What was this? This was 1. It is k plus 1, then minus 1, which gives us k. So you have the numerator, we have k minus 1 multiplied by k. Not writing properly. K minus 1 multiplied by k. This one gives us k because it's k plus 1 minus 1. So this is k. And this other one is k plus 1, k. So the k's cancel. And when the k's cancel, you're left with this. And again, as I said, you go through, listen to it, and pause, and then write properly, and you see what I've just said, what I've explained. So the matrix now is in echelon form. This matrix now is in echelon form. The question is, what would be the value of k so that the result, the system has no result? So the system has no result when the last row is in the form non-zero, 0. No. When the last row is 0, 0, 0, and then non-zero. Non-zero. So that 0 gives us non-zero. If that happens, then the system has no solution. That's what we want. So we want a scenario where this part is 0 and this part is non-zero. Is 0, and this part is non-zero. That's what we want. So once we achieve that, then so when is this part 0? This part is 0 when k is 1, this part will be 0, and when k is -2, this part will be 0. So what about this part? We want to say, will it be non-zero? When k is 1, this part will be 0. This part will be 0. So that means k should not be 1. K is 1, it's not a result. So if it's a result, this system will have solutions. We'll have infinitely many solutions. So what about, let's try this other part. We've already said that when k is -2, this will be 0. What about this other part? This part would be -3. The numerator would be -3, and the denominator would be -1. So that this right side will be non-zero, but the left part is 0. That means the system would have no solutions when k is -2. And somebody will be asking, why I got -2? I look at this numerator, which is already factorized, and equated to 0. Equated to 0. When you put this numerator to 0, you find that k will be k will be 1, and this part k will be -2. That's how I got -2. Now, when does the system have infinitely many solutions? This system would have infinitely many solutions, as you've already said, when k is 1. When k is 1. So infinitely many solutions, we look at this last column, and the system has infinitely many solutions. When you have 0, 0, and this part is also 0, and this part is also 0. When you have 3 zeros here and the 0 here, so that the entire row is of zeros. When the entire row is of zeros, then the system has infinitely many solutions. So you only achieve that when k is 1. So let's move to the next question, because this one we've already answered it. Question 9. Find the condition for these vectors to be linearly independent. So the vectors are linearly independent if we can get scalars ABC such that all those scalars are each 0. So let's see. Just using the definition of linear independent. So we assume we have scalars x, y, z such that this plus this should be 0. So if these scalars x, y, z are all of them zeros, then it means that the vectors are given to us are linearly independent. So I have this. When I open the bracket, I have x plus 0y plus 3z is 0. 5x plus 6y plus 13z is 0. Open the brackets there and then reduce the system to a given form. Reduce the system to a given form. I've already reduced to a given form here, and I know we know how to reduce it, so I'll not go through it. Now, we want value of s so that the system is linearly independent. I look at the last row here. If the last row is entirely zeros, then it will mean the system is linearly dependent. If the last row here is entirely zero, if it's entirely zero, then it means that the system is linearly dependent. So it means for it to be linearly independent, then this element should not be 0. Because we read about 0 here, about 0 here, about 0 here. So you only need to prevent this from being 0. So to prevent that from being 0, we say A out of 3 plus 3 should not be 0. That means A out of 3 should not be negative 3, which means A should not be negative 9. That means A should not be negative 9. And if A is not negative 9, then the system is linearly independent. So A can be anything else but not negative 9. What was the question? Let's go back to the question and see what the question says. The question says, there's a question. The question is here. Yes, the question says, be equal to, for this vectors to be linearly independent. So we found that A should not be equal to negative 9. A should not be equal. Now, this question you can also do it using determinant. And in one of my videos, I've done that using determinant. Now, let's look at this other question. Which of the following sets are subspaces of R3? Subspaces of R3. First, I gave conditions that a subset should satisfy to be a subspace. So the first condition is that that subset should have the 0 vector. Should have the 0 vector. If S is to be a subspace, it should have a 0 vector. And the second condition is that it should satisfy closure, additive closure. It should be closed under addition. That if you pick any 2 elements from this subset and add the 2 elements, the result should be a member of this subset. In other words, should be closed under addition. And then it must also be closed under scalar multiplication. That if you are to pick any scalar and multiply by an element of this set, of this subset, the result should be a member of this subset. So those are the 3 conditions that a subset must satisfy to be a subspace. So now let's go through the subsets given to us and see whether they are subspaces or not. Where there are subspaces, for you to tell that they are subspaces, you show us that they fulfill all the 3 conditions. But where you suspect that it's not a subspace, just give us one example of the condition that is not satisfied. Now, so I'm given a subset A, and this subset A, I see that it's a subspace. It's a subspace. So that means I must show that it fulfills all the conditions. So we claim that A is a subspace, and therefore we show that it fulfills the above conditions. So I go through the conditions and see whether it fulfills. Now, what does this subset mean? What does these conditions mean? It means that A is a subspace and it has vectors. It's a subset with the vectors where the first vector, x, plus twice the second vector gives us thrice the third vector. So that is what we understand from here. That if you're given vectors, like say 1, 2, and then they should be what? They should be 5. They should be 5. So that 1 plus 2 times the second element here should give us this is 5. This will not work. This will not. This is not. This is not in A. This is not in A. What about 1, 1, 3? What about 1, 1, 3? Let's see if it's in A. Let's see if it's in A. 1, plus 2 multiplied by the second element, does it give us 3 multiplied? This would be 1. So that 1 x, which is 1, plus 2y, our y is 2, our y is 1. 2 times 1 should give us 3z, our z is 1. So this vector here is in A. This vector. So A has this kind of vectors. A has this kind of vectors. So our answer is that A is a subspace, vector subspace. So indeed, it has it has this 0 vector. Because you can see that 0 plus 2 0 is 3 0. So that one is there. So the 0 vector is there. It has satisfied the first condition. The second condition, we want to pick any element, any 2 elements, and add them and see what the result is a member of A. We want to pick any 2 elements from A. So I want to pick element P, which is EFG. And I want to say that this EFG satisfies this condition. That the first element, E, plus 2 multiplied by the second element gives me the third element. I want to assume that is true. I also want to pick another element H with this element, this vector H. I want to pick this vector H with these entries, such that I assume it's in A, such that the first element N plus 2 times the second element M will give me the third element multiplied by 3. I want them to satisfy these conditions. So now what I want to pick, I want to confirm is whether P plus H would be a member of A. What is P plus H? I just add these elements, the respective elements, E plus N, F plus M, G plus K. That's what I did. E plus N, F plus M. Now, for P plus H to be in A, it must fulfill this condition. Must fulfill this condition. Let me see whether it fulfills. Let me see whether it fulfills. Let me pick the first 2 elements. E plus N plus 2 multiplied by the second element. What does it do? It's E plus N plus 2F plus 2M. It's supposed to be 2M. Now, so pick the elements of vector P together. The elements of vector P are this, E plus F. Then the elements of vector H together, N plus 2M. Having done that, come back here and see what E plus 2F was. E plus 2F was 3G. And N plus 2M was 3K. And this is the same as 3 into G plus H. So just shown that if we picked any 2 elements, if we picked these 2 elements and added the first element plus twice the second element, the result will be thrice the third element. That's what we've shown. And so that means, therefore, that P plus H are members of A. That's what that means. Now, what remains now is the other fact, the other axiom, the other condition to show that it's closed under scalar multiplication. So again, I pick element P, a vector P, defined above, so that it fulfills that condition given to us, and choose a scalar alpha. Now, so having picked this scalar and this element, we want to multiply alpha and P. When you multiply alpha with these elements of P, you get alpha E, alpha F, alpha G. Let's see whether this plus twice this, the first element plus twice the second element will give us thrice the third element. Let's see if that is true. That's what I'm asking here. So AE plus 2, no, this alpha E plus 2 alpha F is alpha, factored alpha out, E plus 2F. E plus 2F. But what is E plus 2F? E plus 2F is here, is 3G. So this alpha times 3G. In fact, what I'm using here is associativity. And using associativity, this 3 can come out. And I have 3 into alpha G. So what we've just shown is that the first element plus twice the second element gives me thrice the third element. So again, I've said, since the 3 conditions have been satisfied, it means that the subset given to us is a vector subspace. It's a vector subspace. Let's look at this other and see whether it also is a vector subspace or not. If it's not, we just give one example. Vector P, no, this is subset P. We are told subset P consists of vectors whose elements are non-negative. Whose elements are non-negative. So it means it can contain a 0 or any other element positive, but not negative elements. So from that, it tells me that this B cannot be a subspace. Because if I consider a negative scalar like -2 and multiply it by an entry, a vector in B, because B will contain vectors like this, mu, like this mu, which is non-negative entries. It has non-negative entries. So if I take this mu, which is of course in B, and multiply by the negative scalar, I'll get this. And these entries do not satisfy the condition given here. The condition given here is that the elements, the entry should be non-negative. That means that this B, therefore, is not a subspace. It does not fulfill the closure by multiplication of scalars condition. Let's look at part C. We want to see if it's a vector subspace or not. We've been told that it has vectors that have entries where the first entry, but if the second entry is A, then the third will be A plus 1. So that means it has vectors like this. If this is 0 and this is 2, then we expect this to be 3. A plus 1 is 3. So it means this vector, this subspace has no 0 vector. It has no 0 vector. It has no 0 vector because we cannot have a case where it is 0, 0. For example, if this is 0 and this is 0, so this will be our A. Then this will be A plus 1, which is 1. So there is no point where we will have 0, 0, 0. But I've shown that with an example because since we've discovered that it's not a vector subspace, we have to show an example. So we assume that it has a zero vector. So if you assume it has zero vector, then you assume that that zero vector will be equal to 0, a plus 1. So that this 0 equals this 0 will be equal to a, and this 0 will be equal to a plus 1. So in this case, the second entry would mean that a is 0. But the third entry here, this third entry here, 0 plus, which equals to a plus 0, would mean that a is negative 1. So you cannot have the same a being 0 and at the same time being negative 1. So it means if that happens, it means that a does not exist. That a does not exist. You cannot have an a that is 0 and is negative 1 at the same time. That would be a contradiction. So that a does not exist. So that means the vector and then the subset that we've been given is not a subspace since it lacks the zero vector. Let's look at part D. And we want to see whether part D, subset D is also a vector subspace or not. Now, so what the question tells us, there's a condition given here. And the condition is, we are given the entries. So the vector has these entries. So the first entry, the square of the first entry should be equal to the square of the third entry. The square of the first entry should be equal to the square of the third entry. So that means D comprises of vectors like mu, where the square of the first entry equals the square of the third entry. It also comprises of vectors like V here, and you can see because the square of this is the same as square of 1. But now, let's take, because it comprises of mu and V, it has these two vectors. What is the sum of these two vectors? The sum of these two vectors will be 0, 0, 1. No, 0, 0, 2. When you add this, just add the corresponding entries. Add the corresponding entries. So you get 0, 0, 2. Now, does this vector here, does these entries, do these entries satisfy the condition? The first entry, 0 square, is it the same as the third entry square? Is it the same? It's not. That means D is not a vector subspace. Also, we found that this product is not a member of D. This sum here is not a member of D. Let's look at our last question, question 11 of the cut of November 2023. The question is, let this be A, this matrix be A. The condition that A inverse exists is that the constant K should not be equal to. So for A inverse to exist, it means the determinant is not 0. So we did a similar question. So we just want to get this determinant and make it not be equal to 0. Because we said that for A inverse to exist, it means that the determinant should not be equal to 0. So we find this A along column 1. So I just found it along column 1 and we know how to do it. 2 times the determinant of the matrix that remains when you delete first row and second row, no, first row and first column. You have this, then minus, I'm doing it along the first column. doing that because the first column was a 0, so that would make my life easier. So I come here, this is plus minus plus, so that plus 1 here, delete the column, the row of 1 and the column of 1. K minus 325. K minus 325. Of course, this will give us 0. So that gives us K is 1, negative 1.5. Should not be 1, should not be negative 1.6. K should not be negative 1.6. And that is how you're supposed to have done this card. That is a continuous assessment. Just those are very good questions in algebra. And I'll be giving more of these lessons on YouTube. If you've not subscribed to my channel, do that so that whenever I upload more videos, you can instantly get them. Thank you.